Speak on codes and matrix structures, please.
Thank you. First, I would like to thank the organizers for inviting me to this wonderful conference. I'm really grateful. And then, of course, I will congratulate Aron Simis and Stephen Kleiman on their 70th birthday. Really a pleasure to be here. Okay, when you see this topic, I don't know, codes, some of you will say that this has not very much to do with algebraic geometry, or perhaps with algebraic combinatorics, but I will try to show that it has something to do with both of them, could have at least. And so let's start. The talk will be about linear codes, and then on matroids, derived from linear codes. It will be on some Betty numbers for some simplicial complexes, facet ideals of matroids, and codes from algebraic geometry. I'm not sure how, if I will be able to talk on all of this, but we'll see. So what is a linear code? Let FQ be a finite field with Q elements, so Q is a prime power. And N is a positive integer. For many of you, this will of course be well known, but I will introduce it. A linear code, that's a subspace C of FQ to the nth power. So it's a set of words with N letters in each word. And the letters are taken from an alphabet, which is a field. And now we let K denote the dimension of C as a vector space over FQ. So if K is typically then smaller than N, that means that we have a bunch of data which we could have represented as K-tuples, since it's only Q to the K of them. But instead we choose to present them as N-tuples, and that enables us to have some space between them. And that it is a space which we use for error correcting codes, because if you do a small error while transmitting this data, then the wrong word that is received might nevertheless be closer to the correct word than it is to any other of the Q to the K words that sit inside FQ to the nth. And in fact, how much space is there always from one word to the next? That's the next invariant, D, the minimum distance of the code. That's a minimum Hamming distance between two different code words. And the Hamming distance between two words is a number of coordinate positions where they differ. And because of the linearity of the code, it turns out that it's homogeneous in a way, so that a neighborhood around any point is just a translate of the neighborhood around the origin, so to speak. So the minimum distance can always be measured with 0 as one of the code words. And then the distance from x to 0, as you see, let me see, how is it? Yeah, there, that one. That's also called the weight of a code word, the number of coordinates where it's different from 0. Okay. Now we will try to refine this distance concept a little bit. So let's look at DH. That's a number of H-dimensional linear subspaces of C. And of course you can look at it for H range, in the range from, well, 0 also, 1, 2, up to K, which is a dimension of the code. And we then define a concept called the DH, and that is the minimum cardinality of a subspace of dimension H, really. The support of a subspace of dimension H. And what is a support of a subset of FQ to the nth? Well, it's a number. It's a set of coordinate positions where at least one element in this subset is non-zero. So it's really easy to bin the support in some sense, because it is enough that one of the words in that set has a coordinate which is non-zero there. But nevertheless, this gives meaning. It is interesting. So, as an example, what is D1? Well, it's a minimum cardinality of a support of a subspace of dimension 1. But what do the subspaces of dimension 1 look like? They are a constant times a given word. And the support of this entire subspace is equal to the support of this given word. So the minimum cardinality of a support of a one-dimensional subspace is the same as a minimum cardinality of the support of one single word, which we have there. So that's the minimum distance. So we see that the other guys, DH, D2, D3, and so on, they generalize the minimum distance. Now you might wonder, why are we interested in all these DIs or DH or whatever? You see I changed from DH to DI, but that's just an index. Why would one be interested in such a thing? D1, I mean, that's obvious, it's a distance between things. Well, it turns out that if you know all the DIs, then you know a certain profile of the code, which is equivalent to profiles, other profiles of the same code. And this entire profile is something, if you know that, you know certain limitations on the complexity when you are about to do certain decoding processes. I mean, this is something that professional coding theorists know and appreciate. And I think in this setting, we just contend that these are interesting invariants to coding theorists. I mean, there are also a certain cryptological setup called the wiretap channel of type 2, where these DIs will give you the number of bits you have to tap to get important information if you use the code in a slightly, or a generator matrix for the code in a slightly different setting. But that's another story. I just say that it's sort of my basic assumption that these DIs or DH or whatever we call them are interesting. And I hope you can accept it. And a main goal in coding theory is given K and N, construct C such that these DIs are as big as possible. No, that's wrong here. Less ambitious goal for some explicit codes constructing from, for example, from algebraic geometry, say as much as possible about them. Okay, now I'll tell you a little bit of how you can use algebraic geometry to produce codes, linear codes. So let X be any subset of the projective space P, K minus 1, or FQ. For example, the set of all FQ rational points of projective variety defined over FQ. That will be the typical example. And let P1 to Pn be the some of the FQ rational points in general, but typically all the FQ rational points on the variety. Embedded concrete variety in projective space. And for each Pi, you choose coordinates. As you know, they are only defined up to multiplicative constant. And then you define the matrix from these points. You take the coordinates as columns. Each point, a column. That gives you a matrix, which is not entirely determined, since you have this ambiguity in each column that you can multiply with a multiplicative constant. But never mind, you take a representative for each point. And then you take the row space of this matrix. That gives you a linear code. And then the matrix is called the generator matrix of the code. And as you see, I claim that the code parameters are the same up to such equivalence. I mean, all these multiplicative constants. Don't care about them. All the interesting properties that we looked at, they are the same. And this also gives you a feeling of the coding which happens. I mean, what we really are representing are k-tuples that we put in a larger space. So you take the k-tuple as a column, and then you multiply it on the left with this guy, and you get an n-tuple instead, coded information. That's a coding theory. Yeah. Okay. Let's see. Now choose all the FQ rational points on X, let's say that. And now for this variety X, you let JH be the maximum number of FQ rational points on X in a codimension H subspace in the projective space where it lies. I mean, J1 is a maximum number on a hyperplane section of X. J2 is the maximum number on any codimension 2 space. So you sort of scan the variety with all these things, and you look at the maximum result that you get when you scan for each codimension. And then it turns out that this DH gives you that number. That's really only linear algebra when you get into it. Okay, so but certain properties of the variety gives you properties of the code. Dually, if instead we use the G that we looked at, well, as a parity check matrix for C, meaning that it's a coefficient matrix of linear equation cutting out the space that we're looking at. The code is a subspace, and it is given either by generators, as we saw, or by equations. If you let it define the equations instead, then you get another. I mean, if you use the same matrix for equations, then you get another code. That code is an orthogonal complement of this original code. I mean, for the obvious quasi-inner product. Yeah. And if you use the matrix in that way and look at the orthogonal complement, then you get another characterization here. Then you get that di is the smallest t, such that there exists t points of x only spanning a t minus 1 minus I dimensional subspace of pk minus 1. I mean, D1, for instance, is the smallest t, such that there exist t points that only span a t minus 2 space, meaning simply that they are dependent. I mean, we are in projective space now, so if they are independent, t points span a t minus 1 space projectively. So D1 is simply the smallest dependent set among the columns of the matrix that we look at. The cardinality of the smallest dependent set. Okay, well, D2 is the cardinality of the smallest, even more dependent sets. Okay, and examples of codes that one has studied, varieties that one has used in these two ways. The set of FQ rational points of a curve embedded in projective space by some linear system. That's one way to get GOPA codes, which is famous and very well studied. Another case, which I've been into, is that of rational normal scrolls. And then you can have more advanced scrolls, which are projective bundles over curves of higher genus, and Grassmann varieties. And each new variety gives you a new possibilities to scan something and or to look at the secant properties that will solve in the dual way. Yeah. I forgot, yeah. So this, I forgot to say that this reflects the existence of secant properties, which is something we are interested in algebraic geometry. Okay. Now I will change topic a little bit. And I say, in algebraic geometry, you are sometimes interested in what can be obtained from resolutions of something. For instance, the relationship between Hilbert polynomials and Betti numbers and things like that. So, inspired from that, you would like to ask, are there some Betty numbers of something which would somehow determine these DIs that I've been talking about? And that's what I'm aiming at through the next section, which is not exactly algebraic geometry. If I get time, I will come back to some algebraic geometry at the end, but my purpose up till now was to show that properties of algebraic varieties are, to determine them, to know something about them, is instrumental for knowing something about codes when you use a variety to produce codes. That's my point. Okay, matroids initially arose from matrices. That's something I just find evident, at least the word, something which is derived from matrices. And the matroid associated to a matrix M is a pair, E, which is the index set of the columns. It has n columns, this matrix. And I, where I is a set of subsets of E, indexing those sets of columns that are linearly independent. I mean, if you take, for instance, 1, 2, 5 is contained in I if column 1, column 2, and column 5 are independent. Yeah, here you see a matrix. And here you see that E is 1 to 5, and the maximal elements in I, the independent columns, 1, 2, 3, 1, 3, 5, 2, 3, 4, 3, 4, 5. But in addition, of course, all subsets of those are also independent then. So the I, script I, is a set of all subsets of this, including the empty set. I hope I counted correctly here. Yeah. Okay. The elements of such an I then satisfy this, that the empty set is there. And you see that if something is independent, then a subset of it is independent. And in addition, you have this third thing here, that if I2 is bigger than I1, then you can add something from it to get something independent. Okay, so the definition of a matroid is a finite matroid is a pair like this, where I is a set of subsets of E, which satisfies those three properties, which now have been elevated to axioms. And the basis B of a matroid are the maximal elements of I, just like I showed. And they all have the same cardinality, it turns out, which is the rank of the matroid. And the elements of I are called the independent sets. And caution, there are matroids that do not come from matrices. For example, for n is 9, we have, over any field, we have something called a non-Pappus matroid. I'm not sure if that's the smallest, there might be some smaller ones. But this is an example. The dual matroid, then you use a base, or basis, B, and you take the complement of the elements in the original B. In the example we had, you'd get this. And of course, what happened? Yeah, all right. And this is well defined. And the rank then is, of course, n minus the original rank. Now I will show how you make a matroid of a linear code. There are two choices of making it, but I have just chosen one of them. If C is a linear code over a finite field, let M of C be the matroid associated to any parity check matrix of C. For some technical calculations, that will be easier than using the generator matrix. It might sound artificial. Since when K has dimension K, now when C has dimension K, you will find that this the parity check matrix will be have n columns, but n minus K rows, so that the rank of this parity check matrix will of course be n minus K. And K will be n minus the rank of this M, which is what you see here. And then the dual of this matroid, in the sense that we had up there, will actually be the matroid of the dual code, which is an orthogonal complement, and which then corresponds to the generator matrix. So these two kinds of duality match, so to speak. And it turns out that the minimum distance and all higher weights and everything, all the code parameters that we've seen, they're only dependent on properties of the matroid. Okay. Yes. And if you are inside a matroid like this, then the rank of a subset is the largest cardinality of an independent subset of X. And then, of course, rank of the whole matroid is the rank of the whole set E. And the rank satisfies three properties like that. We won't go into, this is just standard matroid theory in an elementary textbook. And it turns out that any function like that, which satisfies these properties, will determine a matroid, so you can elevate also them to axioms for a matroid. And I will then be the set of those I, where rank is equal to the cardinality. Okay? And you can put the dual rank function, defining the dual matroid, will then look like that, it turns out. Okay, just for your information. Okay, now, yes. And it turns out then that the DH is, it's a restatement of what we said about secant properties, really, a while ago. It's a minimum of cardinality of X, such that cardinality of X minus the rank is H. But now I look at the parity check matrix. But you see that this gives meaning, actually, also for matroids in general. Also those not coming from codes. So so we define them that way. That's the DH of a matroid. Now we go to simplicial complexes. A slight change in the topic, perhaps. A simplicial complex on the finite ground set E, that's a subset E, a bunch of subsets, closed undertaking subsets. And I guess one often assumes that the empty set is there. At least it will be in our most interesting examples. So, but you see that the axioms for a simplicial complex is just a subset of the axioms for a matroid. We see in passing. And given such a simplicial complex, you can define its Stanley-Reisner ring over a given field. And that's a polynomial ring with variables, one variable for each element of E. And then you take monomial ideals generated by those monomials indexed by those sigma, which are not in the simplicial complex. I mean, if 1, 2, 5 is not in the simplicial complex, it means that 1x, 2, x, 5 is among the generators. So it is square-free ideal, monomial ideal, like that. And its Stanley-Reisner ring is then R delta divided, R delta is S, S you have up there, divided by I delta. And this ring has a minimal free resolution as an n of E graded or n graded or ungraded module, depending on how much grading you put on it. Where each mi is of the form either indexed by alphas, which are really such simplices, or I mean subsets of E, or by beta, such beta ij. Yeah. This is what is in position I. I mean, mi, exactly, mi. If you remove all grading, you just get a power of s. And the bi alpha are called, and the E graded Betty numbers, and they are 0 if alpha contains is not square free, so to speak. This is something others have also been talking about. And the Betty numbers are independent of the choice of the minimal free resolution, but they are in general dependent on the choice of the field K. And if you just sum up this for all these alphas with cardinality J, you get the twist S of minus J there, the contributions to that twist. And that gives you beta ij. And if you sum up absolutely everything in position I, then you get beta I. So there are 3 levels of beta numbers. Yes, okay. And it's quite obvious that the most graded ones, I mean, these things here, if you know all of them, you know the matroid. In fact, if you know all the beta 1 alpha here, it's clear that this can be taken to be just S. Because this is S divided by something. So this is S in practice. So here are the generators of the ideal. And the generator, I mean, if you know all the generators of the ideal, then you know all the circuits of the matroid. No, wait a minute. Yeah, okay. Wait a minute. I'm getting ahead of myself. Yes, I'm getting ahead of myself, because now I'm turning to this particular simplicial complex, which is a matroid. Yes. Well, in that case, the beta I sigma, beta 1 sigma, which I was talking about, they determine the circuits, the minimal dependent sets which generate the ideal. So that if you know those, you know all the minimal dependent sets of the matroid, and then you know the matroid. So then you know also the DIs that you are interested in. So it's obvious that if you know the most graded Betty numbers, then you know everything about the matroid. On the other hand, if you look to the intermediate level, the n-graded Betty numbers, it's not at all clear that they will determine anything, at least if you haven't studied it for a while. But this is what this theorem says, and it's a joint theorem with Ygg Verdyr, who is a colleague of mine in Tromsø, where we say that the generalized Hamming weights of C can be read off from the n-graded Betty numbers. It's a di is a minimum d, such that beta id is not equal to 0 for each of these things. While, quotients, this might be too technical. My colleague, as I just mentioned, he cautioned me against presenting this quotient because it would only confuse the audience, he said. But in any case, I can tell you that the DI, the beta I, which are ungraded, they are not enough to determine the DI. That, of course, that is certainly something I can say without confusing you. And the DIs, on the other hand, do not determine them. And so on. But let's wait, not talk about the Alexander dual yet. The proof goes via stratifying 2 to the e. I won't present the whole proof, I'll just say something about some ingredients in the proof. you stratify the set of subsets of E according to the nullity, which is the cardinality minus the rank. And it turns out that the nullity is more or less the number of circuits that you can put into something. Roughly speaking, circuit is something dependent, so this is a number of dependencies, which is intuitively what this here says, a number of dependencies, and the number of independent dependencies, so to speak. And then it turns out that, you remember what Ni was? Here it says. Goes with nullity I. And it turns out that beta I sigma is not equal to 0 if this is minimal in Ni. And yeah, you have some more technical information here. And you can also say something about the length then, according to this theorem. And that is, since this nullity can't be more than E minus rank M. And that's what we've called K as the dimension of the code. If we start with the code, that's the dimension of the code. Now this is the length, this is a projective dimension of the resolution. And because of Macaulay'ness of matroids, you knew that in advance, how long it would be. But in any case, you illustrate it here, because you see that since there aren't more code weights than D1 to DK, there cannot be any longer resolution either, given the theorem. Okay. Yeah. So let's look at some examples. A linear NK code that satisfies the minimum distance is less than or equal to n minus k plus 1. And if equality, then the code is called a maximum distance separating. It's as separating as possible. I mean, if you fill a lot of code words into n space, there's a limit to how far away they can get from each other. So if you fill it with something as big as a k-dimensional thing, you cannot get more than n minus k plus 1 for the minimum distance. It's plain, some plain arguments showing that. And but this turns out to be the same as saying that all choices of R columns of the parity check matrix are independent. Where R is n minus k, the redundancy, and also stands for the rank of that matroid. So you get the matroid, the well-known uniform matroid, URN. And you can, for the uniform matroid, you can find the resolution. And then from these twists that you see here, the first one here is R plus 1, showing that the minimum distance is R plus 1. This shows that the minimum distance is R plus 2. No, D2. D2 is R plus 2. D3 is R plus 3. And dk is n. You can read off like that. So the Bettiger diagram, that's another way. Yeah, the Bettiger diagrams, that gives the size of these things up here. But it's flat, it's horizontal, as you see, the Bettiger diagram in this case. But so this is a well-known result, of course, for MDS codes. It's just an illustration of how the theorem works. And so you get the weight hierarchy like that. And here you have another matroid. Here I don't care to specify a code. I just specify a matroid. And you use magma on some field. And you get these things. And then you see that D1 is 2, D2 is 4, and D3 is 6. The smallest twists appearing in each step. So you get that. And another theorem, which is more of a technical kind, if C is a so-called constant weight code, then recently somebody found these higher weights. I mean, what is a constant weight code? This means that all non-zero words has the same weight. That's a very restricted class, but it exists and it is interesting for many coding theorists. And then we, by just playing a little more with these things, we get the resolutions. And you see that this one is pure. Both the uniform matroid and this matroid coming from such codes have pure resolutions. In each step, there is only one summand like that. Well, you saw that in general, you have several summands here. So you don't in general get pure solutions. Resolutions. But for, yes. Okay, so something I haven't said is that how do you get, if you have a code and you have the higher weights of it, how do you get the higher weights of the dual code? Well, it's something called Y duality, which says that if you take first all the k higher weights of a code, and you take n plus 1 minus each of the n minus k higher weights of the dual code, that gives you altogether k numbers plus n minus k numbers, and the union of those numbers is a set 1 to n, the disjoint union then. So in other words, if you know all the weights of the higher weights of a code, you know all the higher weights of a dual code. This is Y duality. But I don't know how you get the resolution and Betty numbers of the dual matroid, given that of the original matroid. That I don't know. Maybe some of you know, but I don't. But we get the higher weights for free if we know those of M. There is also another duality, Alexander duality, which comes into play. The Alexander dual. How much have I left now?
5, 7.
Okay, yeah. Then there is another duality which comes into play. The Alexander dual of a matroid, as we have seen, is EJ. Well, this is of any simplicial complex where J consists of all complements in E of the subsets, not in I. I mean, but this is defined in general for simplicial complexes, as you know. But for a matroid, it looks like this. And let the facet ideal of a matroid be defined by the x, which are in the basis, the maximal independent sets. That's something completely different from what we have seen. Then it turns out that f of m is in fact the Stanley-Reisner ring of another complex, another simplicial complex, which turns out to be the Alexander dual of the simplicial complex of the matroid dual of the original M. So there are two different kinds of duality which do not altogether give you the same thing back. But it's well known, for example, from Egon Reiner, 1980, that for a matroid, in our case, the matroid dual, an n-graded minimal resolution of the Stanley-Reisner ring of the Alexander dual has a particularly nice form. M0 is S, like we've seen, but each mi is not pure, as opposed to for the matroid that we saw earlier in the general cases. Now it's pure and it's linear. So it only, I mean, oof, that's the wrong button. This only increases by 1 or decreases by 1 for each when I increases like that. And of course, here you have the first twist is the generators of the maximal independent sets, and they have a cardinality R, which is the rank of the matroid. So the first which appears here is R. So S is then R minus 1, since we have I is 1 there. So we know that. And we also know the length of this. And the Betty numbers are independent here again of the choice of the field K, even if they are not independent for general simplicial complexes, as we have seen before also, I think, from other lectures. So but then you get some nice Betty numbers here. And my original thought was that these Betty numbers are so nice, you have this much nicer resolution really than from the first resolution we looked at. I thought that these Betty numbers would determine the DIs, and my aim was proving that. And but we found counterexamples. It turns out pretty easily. We find that certainly the higher weights do not determine these beta i's, the last ones. But then we also found counterexamples where the beta i's didn't determine the DIs. You can have things with the same beta i's, but different DIs. And then, just in despair, we looked at this other resolution that I presented to you first. And then it turned out that that resolution with those n-graded beta numbers, that actually gave you the DI. So that was some surprise to us. Yeah. Yeah, but they say something. For instance, they will determine for you the minimum distance of the dual code. So they say something about, if the matroid you start with is derived from a code.
Is there a nice formula for the minimal distance of the star?
Well, I can't give it to you offhand now, but it's given these beta i's, and then you in Egon Reiner you have conversion formulas for the FI's, and I mean if you know the phase numbers. Yeah. I mean, the smallest phase number, which is not equal to all the cardinality of the set of all subsets of that cardinality. Yeah, will give you this. Okay. I think. Well, I thought if I had time, I would show you something about how we determine the higher weights. When the variety you start with is a rational normal scroll. But I think it will be going too far to get into it now, isn't it? Yes. Could get yeah. Well. Yeah, no, it has no sense. I have to make definitions. I skip it. No. Thank you.